fixed point and floating point arithmetic. Leave/decimal.py. The decimal module provides support for fast, correctly rounded decimal floating point arithmetic. It offers several advantages over the float data type. Decimal is based on a floating point model which was designed with people in mind and necessarily has a paramount guiding principle. Computers must provide an arithmetic that works in the same way as the arithmetic that people learn at school. Excerpt from the decimal arithmetic specification. Decimal numbers can be represented exactly. In contrast, numbers like 1.1, 2.2 do not have exact representations in binary for floating point. End users typically would not expect 1.1 plus 2.2 to display as 3.3000000003 as it does with binary floating point. The exactness carries over into arithmetic. In decimal floating point, 0.1 plus 0.1 plus 0.1 minus 0.3 is exactly equal to 0. In binary floating point, the result is 5.55115123125787 minus raised to minus 017. While near to 0, the differences prevent reliable equality testing and differences can accumulate. For this reason, decimal is preferred in accounting applications which have strict equality invariants. The decimal module incorporates a notion of significant places so that 1.30 plus 1.20 is 2.50. The trailing 0 is kept to indicate significance. This is the customary presentation for monetary applications. For multiplication, the school book approach uses all the figures in the multiplicands. For instance, 1.3 into 1.2 gives 1.56, while 1.30 into 1.20 gives 1.5600. Unlike hardware based floating binary floating point, the decimal module has a user alterable precision defaulting to 28 places, which can be as large as needed for a given problem. From decimal import star get context dot prac is equal to 6, decimal 1 divided by decimal 7 is equal to decimal 0.142857. Decimal module. Example 1. Print 0.142857. Get context dot prac is equal to 28 decimal this. Print decimal 1 by decimal 7 this. Precision. Set precision to 6 points. Set precision to 28 points. Output. Yep. Both binary and decimal floating point are implemented in terms of published standards, while the built-in float type exposes only a modest portion of its capabilities. The decimal module exposes all required parts of the standard. When needed, the programmer has full control over rounding and signal handling. This includes an option to enforce exact arithmetic by using exceptions to block any inexact operations. The decimal module was designed to support without prejudice both exact unrounded decimal arithmetic, sometimes called fixed point arithmetic, and rounded floating point arithmetic, excerpt from the decimal arithmetic specification. The module design is centered around three concepts: the decimal number, the context of arithmetic, and signals. The decimal number is immutable. It has a sign, coefficient digits, and an exponent. To preserve significance, the coefficient digits do not truncate trailing zeros. Decimals also include special values such as infinity, minus infinity, and an n. Uh, the standard also differentiates minus 0 from plus 0. Print uh, positive infinity dot format decimal dot infinity. Decimal dot infinity. Okay. Okay. The context of arithmetic is equivalent, specifying precision, rounding rules, limits on exponent, flags indicating the results of operations, and trap enablers which determine whether signals are treated as exceptions. Rounding options include round ceiling, round down, round floor, round half down, round half even, round half up, round up, round 0 5 up. Signals are groups of exceptional conditions arising during the course of computation. Depending on the needs of the application, signals may be ignored, considered as informational, or treated as exceptions. The signals in the decimal module are claimed, invalid operation, division by zero, inexact, rounded, subnormal, overflow, underflow, and float operations. For each signal, there is a flag and a trap enabler. When a signal is encountered, its flag is set to 1. Then, if the trap enabler is set to 1, an exception is raised. Flags are sticky, so the user needs to reset them before monitoring a calculation. See also IBM's General Decimal Arithmetic Specification. The General Decimal Arithmetic Specification. Quick tutorial. The user start to using decimals is importing the module, viewing the current context with get context, and if necessary setting new values for precision rounding or enabled traps. Decimal import get context. Python file example 2. Get context. Print get context. Okay. Print get context. Import name. Okay. Precision 28, rounding round half even. Mean minus 999, Emax 999999. Capitals 1, clamp 0, flags 0, traps, invalid operation, division by 0, overflow. Get context dot precision 7, set a new precision. Print get context. Precision is 7. Decimal instances can be constructed from integers, strings, floats, or tuples. Construction from an integer or a float performs an exact conversion of the value of that integer or float. Decimal numbers include special values such as NaN, which stands for not a number, positive and negative infinity, and minus 0. Decimal 10. Print decimal 10. 10. Decimal 3.4. Print decimal 3.4. Decimal 3.14. Float. Decimal 0. Print decimal 0 314 minus 2. Decimal string 2.0 power 5. 1.41. Decimal 2 power decimal 0.5. Decimal NaN. NaN. Decimal infinity, negative infinity. If float operation signal is trapped, accidental mixing of decimals and floats in constructors or ordering comparisons raises an exception. C is equal to context, C traps float operation is equal to true. Decimal 3.14. Print float operation trap exception float operation decimal dot float operation class decimal float operation. Again, the significance of a new decimal is determined solely by the number of digits input. Context, precision, and rounding only come into play during arithmetic operations. Get context. Get context. Decimal 36. 3.0, 3.0, decimal this, decimal this plus this, friends, 5 pointers. Get context dot rounding, round up, rounding up, decimal 88. In the internal limits of C version are exceed if the internal limits of C version are exceeded, constructing a decimal raises invalid operation. Decimal try, catch, decimal dot invalid operation as invalid operation, print accept. Decimals interact well with much of the rest of Python. Here is a small decimal floating flying circus. From decimal module import decimal max data, print max data of this equal to this dot format data comma max data. Minimum data. Data. Max data is equal to max data mean data. equal to mean data. Mean data 0.3. Sorted data. Print sorted data. Format sorted data 0.03, 1.0, 1.34, like that. Some data. Print sum of data equal to dot format sum data. ABC is equal to data 3. Print split data. Split first 3 data. Dot format split data 3. STRA store STRA A is equal to STRA just A. What do we do? Okay, float A. Print A is equal to this dot format A float A. This round A1. Print A is equal to round A comma 1 is equal to this dot format 1.3 integer A. Print integer A dot format format 1 A into 5. Print A into 5 is equal to dot format 6.70. A into B. Print A into B equal to dot format print A is equal to A comma B is equal to B comma C is equal to C dot format A comma B comma C. C mod A equal to dot format C mod A 0.77. And some mathematical functions are also available to decimal. Get context example 3. From decimal import decimal. Get context dot comma get context. Precision is equal to this decimal to dot square root. Print a square root of decimal 2 equal to dot format decimal 2 square root to decimal 1 exponent decimal 1 exponent decimal of 1 equal to dot format decimal 1 exponent decimal 10 ln. Print ln logarithm of decimal 10 equal to dot format decimal 10 ln 2.30 decimal 10 log 10. Print log 10 of decimal 10 is equal to dot format decimal 10 log 10 1. The quantized method rounds a number to a fixed exponent. This method is useful for monetary applications that often round results to a fixed number of places. Decimal quantize number 7.235 equal to dot format round down. Import this now. 7.32 3 to 5 rounding up. Print by rounding down. Quantize number by rounding up. 7.325 equal this dot format is number 8. As shown above, the getContext function accesses the current context and allows the settings to be changed. This approach meets the needs of most applications. For more advanced work, it may be useful to create alternate context using the context constructor to make an alternate active Alternatively, use the set context function. In accordance with the standard, the decimal module provides two ready to use standard context, basic context and extended context. The former is especially useful for debugging because many of the traps are enabled. My other context example for from decimal import star. My other context precision 60 rounding half down set context mother context print 0 point this extended context print extended context 9 set context extended context decimal 1/7 this decimal 12.0 infinity set context basic context decimal 42/0 to throw an error decimal division by 0. Context also have signal flags for monitoring exceptional conditions encountered during computations. The flags remain set until explicitly cleared, so it is best to clear the flags before each set of monitored computations by using the clear flags method. Set context, clear flags. Clear flags. Try. Accept decimal dot division by 0 as division by 0 print tb set 3.1492 get context print get context the flags entry shows that the rational approximations to pi was rounded digits beyond the context precision were thrown away and the result is inexact. Some of the discarded digits were non-zero. Individual traps are reset using the dictionary in the traps attribute of the context. Set context decimal. Example 5 from decimal import star print exception infinity get context dot traps division by 0 is equal to 1. Now it will trap print this, right? Most programs adjust the current context only once at the beginning of the program, and in many applications data is converted to decimal with a single cast inside a loop. With context set and decimals created, the bulk of the program manipulates the data no differently than with other Python numeric types. Thank you.